In this video, we are looking at more examples of sequences. We're trying to determine whether these sequences converge or diverge, and I will introduce a couple of theorems as we go through the more advanced examples. So here's our first theorem. It says, let L be a real number, and then let f be a function of a real variable, such that the limit as x approaches infinity of f of x equals L. If a sub n is a sequence such that f of n equals a sub n for every n in the natural numbers, then as n goes to infinity, a sub n also approaches L. So this sequence converges to L. Now that is a lot of notation. Let's try to make some sense of it. So it says L is a number and f is a function of a real variable such that if we take the limit as x goes to infinity, the function approaches L. So I don't know exactly what this function looks like, but it could very well look like this. Here's y equals f of x. Here's the horizontal line, y equals L. And maybe it looks like this. That could very well be y equals f of x. And L is a real number, so this is what we would see, something like this. Now this says, if a sub n is a sequence such that f of n equals a sub n, well, what does that mean? Well, that just means that f of x and f of n, they're exactly the same. So a sub n, those are y values on the graph of y equals f of x. When n equals 1, we get f of 1. When n equals 2, we get f of 2. When n equals 3, we get f of 3, and so on. So when n is 1, we would get f of 1, which is right there. When n is 2, we get f of 2, which is right there. When n is 3, we get f of 3. When n is 4, we get f of 4. When n is 5, we get f of 5. When n is 6, we get f of 6. N is 7, 8, and so on. This theorem says that if this happens, so you have some function and as x goes to infinity, the y values in the function approach L. It's a continuous function. It's a Calc 1 function, a function that we can take the limit of. This says if the points of the sequence lie on that curve, then of course those points are going to approach L too as n goes to infinity. They're going to approach L as well. So all those points are lying on the curve and they're getting close to L as n goes to infinity because f of x gets close to L as n goes to infinity. And we take advantage of this fact a lot whenever we want to use L'Hopital's rule or something like that to evaluate a limit. Now you cannot technically evaluate a limit using L'Hopital's rule for this sequence of points for a sub n, because I can't take the derivative of something like that or the derivative of something like that. It doesn't make sense to even talk about a derivative of a point. But I can say, according to this theorem, the limit as n goes to infinity of a sub n is equal to the limit as x goes to infinity of f of x, where all the n's are just replaced with x's. And then if this limit exists, then this limit exists. So we're going to take advantage of that a lot. We'll take advantage of it right here. So here's our first example. Now the Larson text actually skims over the derivation of this limit. It turns out that the limit does exist and it converges to E, but they refer back to a result that they came up with in 5.6, section 5.6 in the text. We could do that. I'm not going to do that. I'm going to show you where it comes from. So let's say I want to determine if this sequence converges or diverges. Well, one way to do that is to take the limit as n goes to infinity of 1 plus 1 over n, all raised to the n. Now notice if I substitute in a large number for n, this is 1 over something really large, that's really small. So this expression in parentheses approaches 1 because this is going to 0 and that's going to 1 and 1 plus 0 is 1. So we have a 1 in here. and the exponent is going to infinity. So this is a 1 to the infinity indeterminate form. And we discussed when we studied L'Hopital's rule in Calculus 1 that this can be evaluated by getting that exponent down here. And we can get that exponent down here by taking the log of this thing. Now, if I want to find the value of the limit, and I want to take the log of this, I also have to take the log of the limit. So I'm going to let y equal the limit, provided the limit exists. And then let's take the natural log of both sides. So the natural log of y on this side equals the natural log of this limit on this side. There's not very much space, but there's a little tiny ln over there. Now this function is not continuous, but if I change those n's to x's, and I can because of this limit, that function is continuous. Now since this is the log of a continuous function, I can bring the log inside the limit. So now I've got this. And remember from algebra, if you have log of a to the n, you can bring that n out front. That's n times natural log of a. That's totally legal. We're allowed to do that here. And so now I have x times natural log of 1 plus 1 over x, which is x to the negative 1. And I may still have an indeterminate form. All of this is equal to natural log of y, where y is the limit. Okay, so as x goes to infinity, this goes to infinity. As x goes to infinity, this guy goes to 0, and I get natural log of 1, which is also approaching 0. So this is an infinity times 0 indeterminate form. And that's another one that has to be handled with L'Hopital's rule. We're not quite ready for L'Hopital's rule yet, because in order to use L'Hopital's rule, remember we need an infinity over an infinity, or a 0 over 0. Well, just in case you've forgotten, here's L'Hopital's rule. If you're taking the limit as x approaches a number, and in this case it's infinity, so I'm just going to use that special case, of f of x over g of x, and this is a 0 over 0 indeterminate form, or this is a plus or minus infinity over infinity indeterminate form. If either one of those is true, then according to L'Hopital's rule, we usually put a little h over the equal sign when we invoke L'Hopital's rule. That limit is equal to this limit. You take the derivative of the numerator and the derivative of the denominator, and you evaluate that limit instead. Now this only works if you have 0 over 0, or plus or minus infinity over plus or minus infinity. But if I've got an infinity times 0, it turns out I can always rewrite that as 0 over 0, or infinity over infinity, by moving one of these to the denominator and taking its reciprocal. I know it seems a little strange, but I'm going to leave the logarithm in the numerator, and in the denominator, I can't put an x down there because that wouldn't be equivalent, but I'm going to divide by 1 over x. And when I divide by 1 over x, isn't that the same as multiplying by the reciprocal? If I flip that and multiply, I get that back. So this is exactly the same as that. Now, as x goes to infinity, this approaches 0. This is approaching 0, so I have natural log of 1, which is 0. So this is now a 0 over 0 indeterminate form, which means I get to use L'Hopital's rule. So according to L'Hopital's rule, we take the derivative of the numerator and the derivative of the denominator, and that is equal to this limit over here, which is very nice. Works out great for us. Oops. Try to get some scratch paper that It's clean enough to finish this problem, but I don't want to get brand new paper. Go through so many trees every semester. All right, so we were here. And I've got derivative of the numerator. The derivative of the numerator is 1 over, the derivative of log of something is 1 over the inside function times the derivative of the inside by the chain rule. And the derivative of x to the negative 1, I think I'm just going to leave that alone for right now. Now, according to L'Hopital's rule, this limit over here is the same as this limit, and this limit is the same as this limit. Let's look at it. Derivative of a 1 is 0. So this is the derivative of x to the negative 1 plus 0 divided by the derivative of x to the negative 1 plus 0. So these guys are actually exactly the same. I don't even have to evaluate those derivatives. They reduce, and we get this guy. As x goes to infinity, this is 1 over something really large. So that is really small, and we get 1. But that is not the value of the limit. Because remember, all the way back when we started this problem, we said y was equal to this limit, and let's take the natural log of y to get that exponent out of the exponent and in front of a logarithm. So log of our limit is 1. So if I want to get y by itself, which is the limit, I'd use e to this power equals e to that power. It's just a property of exponents and logs. These two undo each other, and we just get y equals e. So that is the limit as x goes to infinity of 1 plus 1 over x raised to the x. And because of our continuous function theorem, that's the same as this limit. So that means this sequence converges to e. Which I think is pretty cool. Okay. Now that technique is not a technique that you'll have to use very often, but occasionally it comes up, and it's definitely an advanced form of, or an advanced example of L'Hopital's rule. So does this one converge? Yes, it converges. A sub n converges to e. All right. Now let's look at some other examples. So here's an example. Someone might say a sub n is n cubed over 3 to the n plus 6n. Now determine if this sequence converges or diverges. So first of all, I notice that if I take the limit as x goes, or n goes to infinity, of n cubed over 3 to the n plus 6n, I have an infinity over infinity indeterminate form. So I want to use L'Hopital's rule, but I can't use L'Hopital's rule for this because this is just a bunch of points. When I graph them, it looks something like that, and I can't take the derivative of a point. So we're just going to get around that by changing to x. We're going to have a continuous function that behaves just like our function. As x goes to infinity, n does the same thing because these are points on the curve. It's given by this continuous function f of x equals x cubed over 3 to the x plus 6x. We still have infinity over infinity, but we can use L'Hopital's rule. Take the derivative of the numerator and the derivative of the denominator. Derivative of 3 to the x is exactly the same exponential times log of the base. Derivative of 6x is just 6. Question is it still infinity over infinity? Yes, as x goes to infinity, 3 to the x still goes to infinity, and x squared still goes to infinity. So we've got to use L'Hopital's rule again. We have 6x this time. And then when I multiply by another, when I take the derivative of this again, I have to multiply by another natural log of 3. So we already had a natural log of 3. We take the derivative again, we get another one. So you have natural log of 3 squared. Derivative of 6 is 0. Do I still have infinity over infinity? It turns out I do. One more time. Derivative of 6x is 6. Derivative of this expression in the denominator is going to give me another natural log of 3. All right. Now, I don't have infinity over infinity anymore, which is a very good thing, but now I have to evaluate this limit. Don't just keep taking derivatives. If it's not infinity over infinity or 0 over 0, you cannot use L'Hopital's rule. And at this point, 6 does not approach infinity. 6 approaches 6 as x approaches 6, or as x approaches infinity. So now I've got 6 divided by a very large number, because 3 to a very large power is a very large number, and that's just a constant. So 6 over a large number is going to be a small number, so the limit is 0. So we'll say that this sequence converges to 0. All right, let's look at this one. As n goes to infinity, natural log of n also goes to infinity. Same thing happens with n cubed. So this is another infinity over infinity indeterminate form. So I'm going to change my n's to x's and use L'Hopital's rule where I can. Now careful here, a lot of students want to bring this 2 down because they're familiar with this rule. Natural log of a to the n is n times natural log of a. First of all, I want to say if you tried to use that rule, I love that, because that means you're remembering this fact and you're using these types of facts to simplify expressions like this. That's a great idea. But this has parentheses implied there. This is natural log of a raised to the n, not natural log of a raised to the n. Like the log, the n is applied to the a, not the log of a. Here, this is the log of x squared, so I can't bring the 2 out front. But with my infinity over infinity indeterminate form, I can use L'Hopital's rule. So according to L'Hopital's rule, I take the derivative of the numerator. And that requires the chain rule because I have this function inside the squaring function. The derivative of something squared is 2 times that something times the derivative of the inside. Well, the something is natural log, and the derivative of natural log of x is 1 over x. And then let's multiply or divide by the derivative of x cubed, which is 3x squared. Okay, now this simplifies. Multiplying by 1 over x up here is the same as just multiplying by an extra x in the denominator, so we get this. X squared times an extra x is going to give us an x cubed. So this is an infinity over infinity indeterminate form again, because as x goes to infinity, natural log of x goes to infinity. Of course, x cubed goes to infinity. So we'll take the derivative of the numerator and denominator again. Derivative of natural log of x is 1 over x. Derivative of 3x cubed is 9x squared. So we end up with this. That x comes down here, we end up with a 9x cubed down there. So as x goes to infinity, I have 2 over something really large, which is really small. It's 0. It's a coincidence that it happens to be 0. They're not all equal to 0. So remember, big picture, our sequence is approaching 0. So I don't know exactly what it looks like, but eventually it looks like that. Approximately, toward the end, it looks like that. Okay. Now for this next limit, you have to use a fact from Calculus 1, excuse me. And that is, if you've got a continuous function and you've got a continuous function inside a continuous function, so a composition of continuous functions. It turns out you can bring the limit inside. Like, that's perfectly legal. So if I want to take the limit of this as n goes to infinity of this, it turns out the 3 I'm thinking of as a constant, the 4 I'm thinking of as a constant, I can just take the limit of that exponent. And if 4 to that limit exists, if everything is continuous, then like that's the answer. Then we're done. And here's the limit law. It's really the limit of 3 is 3 minus, and then we can bring that limit inside this function, minus 4 raised to the limit of, as n goes to infinity, of 1 over n. I know it looks weird and complicated, but basically it's just allowing me to take the limit as n goes to infinity of that and then put all the pieces together when I'm done. And as n goes to infinity, this guy goes to 0. 4 to the 0 is 1. So I've got 3 minus 1, which is 2. So my sequence, a sub n, converges to 2. All right. I think we'll probably do just a few more of these. Here's another one. I've got a sine function with this function of n inside. Obviously, this is not continuous, but if I change from n's to x's, it's continuous. Continuous where it's well defined. So I have the sine of this. You can bring the limit inside. And that's an infinity over infinity indeterminate form. But it's the kind of infinity over infinity indeterminate form that we talked about before. We could switch from n's to x's and use L'Hopital's rule. That would be legal. Or since it's a polynomial over a polynomial, I'm going to do what I did at the beginning of Calc 1. I'm just going to divide by the highest power of n in the denominator, which is a 1, n to the first. So when I divide everything by n to the first, I get this. 2 pi n over n is just 2 pi. 3n over n is 3, and then I've got a 1 over n over there. Okay. And as n goes to infinity, this guy goes to 0, and we end up with sine of 2 pi over 3. And maybe you've forgotten, 2 pi over 3 is 120 degrees. Pi over 3 is 60. So opposite the 60, there's a square root of 3. That's a 1, 2 square root of 3 triangle. X is negative, though, because we're in quadrant 2. But sine is opposite over hypotenuse. So this is square root of 3 over 2. So it turns out that the sequence, if I were to graph all these points, the y values are approaching, the sequence values are approaching y equals square root of 3 over 2. Now the next fact comes up pretty often, and it's something that will be useful in your homework. I don't believe it's outlined explicitly in your book, but I've seen it in other textbooks. I'm going to call it the r to the n theorem. Here's the idea. If r is a constant, and you're taking the limit as n goes to infinity of r to the n, you get different values in different cases. If r equals 1, excuse me. Excuse me. Wow. Okay. If r equals 1, this is 1 to the nth power. 1 to any power is just 1. So in that case, the limit it goes to infinity is 1. Now if r is between 0 and 1, or actually if r is any fraction, any proper fraction, so r could be a positive fraction or negative fraction, but we want its absolute value to be between -1 and 1. So it's some part of a whole, plus or minus 1. Let's say like r equals 1/2, for example, 1/2 to the n. Oops, that's a sequence. The sequence 1/2 to the n looks like this. When n equals 1, I get 1/2. When n equals 2, I get 1/2 squared, which is 1/4. I can also think of that as half of a half. So 1/2 times 1/2 is 1/4. And half of that is 1/8. And half of that is 1/16. And then I can multiply by 1/2 again, and I can get 1/32. As I keep taking fractions of fractions of fractions of fractions, these are getting smaller and smaller and smaller. They're never actually going to get to 0, but I can get very close to 0, as close as I want to 0. So whenever r is a proper fraction, positive or negative, it turns out that the limit is going to be 1, or excuse me, limit is going to be 0. Because as we take half of half of half of half of half, and we keep going, eventually we're going to get something that's arbitrarily close to 0. Now if r is -1, I think we already know how this is going to behave. We looked at that example in the first video with -1 to the n plus 1. But the sequence for r equals -1 looks like this. When n is 1, we get -1. When n is 2, we get 1. 3, -1 cubed is -1. When n is 4, -1 to the 4th is +1, -1 to the 5th is -1, -1 to the 6th is 1, and you just keep going infinitely, forever. That's oscillating between 1 and -1, just like we saw before. -1, 1, -1, 1, -1, 1. The other one that we did started at 1 and went to -1. This one just starts at -1 and then goes to 1. So we've got two sequences, or two subsequences that approach different numbers. These guys are all approaching 1, and these guys are all approaching -1. So if r equals -1, the limit does not exist. And if the absolute value of r is greater than 1, I think you can imagine what happens. If r equals 2, let's say we've got 2 to the n, that's our sequence. I've got 2, and then I double it to get 4, and then I double it to get 8, and I double that to get 16, and double that to get 32, and I just keep going. It's just getting larger and larger and larger. So this doesn't exist. It doesn't exist in a special way. The limit's going to be infinite. But I'm just going to write dne right here. I'm sorry about the hybrid notation. I don't usually like to say this limit equals dne, but I'm just going to write it like that for shorthand. But if the absolute value of r is greater than 1, if r is positive, I get something that goes off to infinity. Let's see what happens if r is negative. Then I get -2, +4, -8, +16, -32. It's the same absolute value, same magnitude, but that sign is flipping the whole time. So we've got -2, +4, -8, and then 16. So half the time it looks like 2 to the x. The other half the time it looks like 2 to the, or -2 to the x, because I've multiplied out here by -1. So it's growing, it's going to infinity half the time. The other half the time it's going to -infinity. So, and it's because we're multiplying this by this number that's greater than 1. So the magnitude is going to get larger and larger and larger. And that's going to be true for any value, not just 2, that's greater than 1, or whose absolute value is greater than 1. So that's the r to the n theorem. It comes in handy throughout this chapter, so we may refer back to it. Okay. I think I just want to do a few more examples, and then we'll wrap up this video. Okay, so let's say this is our sequence. Someone says, determine whether this sequence converges or diverges. You say, I would love to, but look at that square root. As n goes to infinity, 2 times something large is something large, so I get infinity. A large number squared is still large. Add 1, still large. Take the square root, it's not as large, but it's still large. So we get an infinity over infinity indeterminate form. Now with this one, you could change from n to x and use L'Hopital's rule, but I think it's simpler if you do this. Now, I would really love to divide the numerator and denominator by the same thing. That's what we did when this was just an n squared plus 1 and a 2n. I would divide by the highest power of n in the denominator. So I would divide everything, if the square root wasn't there, I'd divide everything by n squared and I get my limit. But that's not the best way to handle this because I've got the square root. And you can't just square everything either because then you're going to find the limit of the squared a sub n's, not the limit of a sub n. So we got to do something else. This is what we do. In order to make this look like that polynomial over a polynomial that I'm comfortable with, that I know how to evaluate the limit of, I square this. And that's legal. That's totally fine, as long as I also take the square root. Because if I square something and I take the square root and that something is positive, and it is positive because n's going to infinity, and this we are assuming is well defined for n equals 1, 2, 3, for all those positive n's. This is the same as the 2n that was there before. And now, because of our properties of square roots, I've got square root of a over square root of b. I can write that all under one root. And then this a over b, that expression, that's going to be something like what I'm used to dealing with. So let's do that. We've got the limit as n goes to infinity of square root of all this. 2n quantity squared, square the 2, square the n, gives you 4n squared. Down here you've got n squared plus 1. And we're going to divide the numerator and denominator by the highest power of n in the denominator, just like we did in Calc 1. And the n squareds reduce up here, we just get a 4. N squared over n squared is 1 plus 1 over n squared. 1 over something really large squared is going to 0. So 1 over something large is something small. And so I've got the square root of 4 over 1, or square root of 4, which is 2. What does that mean? That means that this sequence, if I were to graph it and then look at all the points, those points are getting closer to the line y equals 2. And we say that this converges to 2. I don't know exactly what it looks like, but it might look like this. Here's y equals 2. Something like that. Okay. Now on this one, maybe somebody gives you this sequence and they say, does that converge or diverge? Well, I've got an infinity over infinity indeterminate form again. Because 3 to a really large power is a really large number. 4 to a really large power is also a really large number. So I need to do a little bit more. I can switch all the n's to x's and use L'Hopital's rule. But I want to do something different. I want to do something similar to what I did here. I think it's more elegant than using L'Hopital's rule for everything. But I don't have powers of n here. Or I don't have powers of n down here. I've got powers of 3 and powers of 4. But I want to do something similar here. Let's think about why this worked. The reason why we always divide by the highest power of n in the denominator is that when we do that, this n squared over n squared gives us a 1. And that means if I'm dividing by the highest power of n in the denominator, I get a constant plus a bunch of things like 1 over n squared, 2 over n, things like that, that all go to 0. because this power of n is going to be larger in the denominator for all of them except for that one that had the same power of n in it, that gave us that constant. So thinking similarly over here, the problem is the 3 to the n and the 4 to the n. I'd really like to get rid of those, because if I could get rid of those, one of these, I'd get rid of the infinity over infinity. There's actually negative infinity in the denominator. So I'm gonna do the same thing that I did over here. Same idea, just applied slightly differently. Math people do this all the time. Like, I know this worked for something else. What if you ask yourself, will it work for this? And it turns out that it does. So I'm going to divide the numerator and denominator by 4 to the n and use some exponent properties. And my hope is that because I divided everything by 4 to the n, I'll have a bunch of things that go to 0, constants in some places, and I'll be able to infer what the limit is. So here I've got 3 to the n over 4 to the n plus 2 over 4 to the n, all divided by 6 over 4 to the n minus 4 to the n over itself, which is 1. Now, as n goes to infinity, this is 2 over a really large number, so that's a very small number. 6 over a very large number, that's a very small number. Careful here, you've got a 3 to the n and a 4 to the n, so that's another infinity over infinity indeterminate form, divided by a negative 1. But I can use exponent properties to rewrite that. Remember this? If you've got a to the n over b to the n, that's the same as a over b to the n. Now, most of the time in the other class, algebra class, we would take something that looked like this, and we would apply the nth power to the numerator and denominator and get this. This time we're using this rule in the reverse. Instead of going this way, we're going this way. So I see the 3 to the n over 4 to the n, and I think, let's make that 3 over 4 to the n, dividing by negative 1. So I can factor the negative 1 outside of my limits, just a constant. And now I can use my r to the n theorem that we talked about. If I've got 3/4 and I take 3/4 of that, and then I take 3/4 of that again, and I keep taking 3/4 and 3/4 and 3/4 over and over again, because I keep taking fractions of what I had before, I'm going to get 0. So this is going to go to 0, and then multiply 0 by negative 1, and I get 0. So this sequence converges to this limit, which happens to be 0. And we're good. We're done. All right. Now let's do 2 more examples, and then we'll call it a video. We'll see each other in another video. Now these 2 involve factorials. Now remember how factorials work, how they're defined. If I have 5 factorial, all that means is that's 5 times 4 times 3 times 2 times 1. Now there are lots of interesting properties to factorials. This is involved typically in counting problems. Like, let's say I have 5 chairs at my dinner table. You might say, how many different ways can I assign 5 people to those 5 chairs? Well, I have 5 possibilities for the first chair and 4 possibilities for the second chair, because I already used one of the people. And then 3 possibilities for the third, and then 2 possibilities for the fourth, and then there's only one guy left. He has to sit there. The number of ways I could arrange those people at the table is 5 times 4 times 3 times 2. Which is a lot, which is 120 different ways I could arrange my friends at a dinner party at this table. But that's not what we're doing here. What we're doing here is we're looking at something that looks like this, and we're calculating, or some sequence that looks like this, and we're trying to determine whether that sequence converges or diverges. So remember that this is how it works. So So if you see n factorial, what that means is start with n, and then subtract 1 and multiply, and subtract 1 and multiply again, and keep going until you get down to 3 times 2 times 1. We're going to do the same thing over here. If I distribute that 2 times n is 2n, 2 times 3 is 6. The way to simplify this is to think about which of these two numbers is larger. Is 2n larger or is 2n plus 6 larger? I hope you said 2n plus 6 is larger because of the plus 6. Because of that, because this one's larger, a bunch of the factors in the numerator and factors in the denominator are going to cancel. All the factors in the numerator are going to cancel, and then there are going to be some leftover factors in the denominator. Just to show you what I mean, let's do a simpler example. Let's look at n factorial over n plus 1. And let's do it for a fixed n. Let's just say n equals 4. So this is 4 factorial over 5 factorial, if I just substitute here. Now remember what that means. That's 4 times 3 times 2 times 1 over 5 factorial is 5 times 4 times 3 times 2 times 1. You see the one that has a larger number that you're taking the factorial of? It has all the factors of that smaller number in it, that smaller factorial. So 4, 3, 2, 1, those factors cancel with all of those factors. So we're actually left with 1/5. Something similar is going to happen here. Now, I want to simplify this in general. I said, well, that's 1/5 for 4 factorial over 5 factorial, but what about this? What about this in general? Well, I'm going to take the larger one and say that's n plus 1 times 1 less than that, that's n. And then everything after that is the rest of n factorial, so that's n factorial and n factorial. So those reduce and we end up with 1 over n plus 1, which is exactly what we had here. N was 4, so I've got 1 over 4 plus 1, or 1/5. There's only the one number left over, just like here there's only the one number left over. Now here I got a 2n and a 2n plus 6, so I think I'm going to have 6 numbers left over. It's kind of expanded. But that's because of this distribution of the 2. 2 times the n gave us the 2n. 2 times the 3 gave us the 6. You can't just take the factorial of 2 and n plus 3. It just doesn't work that way. Same thing here. So I'm going to leave the numerator alone. In the denominator, I'm going to start with 2n plus 6, then multiply by 2n plus 5, then 2n plus 4, and 2n plus 3, and 2n plus 2, and 2n plus 1. Finally, 2n, and everything after that is 2n factorial. So those are going to reduce. Yay! So I have 1 over this. As n goes to infinity, that denominator is clearly getting very large as this numerator stays a 1. So we get 0. So that means our sequence, which looks like this, converges to 0. Now this next one looks very similar, but be careful, it's not exactly the same. I've got an n and an n minus 3 factorial. The n minus 3 is smaller. So rather than expanding this one and trying to get an n factorial out of it, I have to expand this one. And if you don't believe me, you should always just try plugging in values for n. So let's substitute n equals 4 into this. So 4 factorial over 4 minus 1 is, or 4 minus 3 is 1 factorial. So I have 4 times 3 times 2 times 1 over 1. Well, only a 1 canceled, which isn't much. So let's do n equals 6. 6 factorial over 6 minus 3 factorial. 6 minus 3 is 3. So I end up with 6 times 5 times 4 times 3 times 2 times 1, all divided by 3 times 2 times 1. Those reduce and those reduce. And now I've got 6 times 20, or 120. So, okay, we're looking for a general pattern here. Let's see, what was the pattern? Well, it looks like I had 3 numbers left over, but they weren't in the denominator, they were in the numerator. And I think that makes sense because n minus 3 is 3 less than this. So all of these should cancel with all of these except for the first 3. So I'm going to expand the one that has the larger value in front of the factorial. N is larger than n minus 3. So I'm going to call that n times n minus 1 times n minus 2 times n minus 3 and everything after that, so factorial. Looks like we're really excited. I actually am. I'm excited. This is n minus 3 factorial is going to reduce. Bam! All right. Now I've got this times that. What happens as n goes to infinity? Something large times something large minus 1 times something large minus 2. Those are 3 large numbers multiplied together. We get a large number. So this expression, which looked very similar to the last one that converged to 0, this one diverges to infinity. So that's how that goes. And I think that's going to be it for this video. We'll look at a couple of other theorems that involve sequences in the next 2 videos. We're going to look at monotonic bounded sequences. We're going to look at the squeeze theorem. We have an absolute value theorem in your textbook as well. So we'll discuss all of those, and then we'll apply them to some sequences. And then maybe we'll do a real-world example or 2, so that you can see that this is not just strange little points on the xy plane. This actually represents things. These sequences represent meaningful objects because lots of things are discrete. Lots of things don't come in tiny parts or infinitely many continuous interval of tiny parts. There are many quantities that you're just counting one thing at a time. So sequences would be appropriate for that.